Okay, let's take a look at a convolutional neural network. And this is, I think, a really good neural network to start with and trying to understand the inner workings of the neural networks that underlie artificial intelligence. And that's in part because it functions most commonly on the process that's shown here, which is an image classification. And I think these are easy to wrap one's head around. So the neural network here is given a picture and it's classifying that picture um, as one of many possible outputs. So, what we're going to look at is the process of inference, which is what is done after a neural network is trained. And so that process takes a new image that the neural network has not seen before, sends it through these processes, and ends with classifying a probability of what it's likely to be. So, building off some great visualization tools that are out there and adding one to the list, we'll walk through what each of these steps looks like inside the neural network. So, one of those methods listed there is pooling. And this, when displayed with color coding and simple integer values, becomes pretty easy to understand. So, the matrix on the left is a 4 by 4 matrix, and it's being condensed down to a 2 by 2 matrix on the right. And if you look at the blue top right corner, you can see that those four numbers are simply being averaged to fill in a 3 at the top right in the case of average pooling, or that the maximum of those values is being placed into the corresponding top right in the case of max pooling. And so each of those quadrants is treated the same to get those results. The convolutional layer itself is a process of scanning across, in this case, an image. And in a simple case, if we had a 5 by 5 uh, matrix as the input, and it had simple 0 or 1 values, and we applied a filter that we were looking for a match across that image, and it was a 3 by 3, we would then scan that across, starting in the top left and moving to the right. And at each of those steps, we would evaluate what the overlap in that filter was to the input and then fill that in as the value into the output. The other functions that are in this operation include the rectified linear unit activation. This is what makes the neural network nonlinear and gives it some of its interesting properties. And in this case, the function is simply to pass a value of 0 if it's given a negative input, or if it's given a positive input to pass that same value as the output. And then probably the most complicated, and this is what does the final step of classification by giving a probability in an output, is done by the softmax function, which takes e raised to the value of an input and divides that by the sum of all of the possible inputs, each being used to raise e to the power of that value. That converts these input values, -1, 0, 3, and 5, into a probability score, which can be used in classifying, for example, an image. So this CNN explainer, which is the inspiration for the network that I'll walk through in a little more detail, is a great visual explainer of how a neural network works. This is walks through the process of inference for a CNN, and it allows you to select from a series of images at the top. So this website, if you click through to it, is a live neural network. It's a small, by modern standards, neural network, 7,000 parameters and 17 layers. And you can pick any of the images that are on the top bar, or you can upload your own image. And it takes the image, breaks it down into the 3 color channels, and then it performs those operations that we were just looking at. They're going to look a little more complicated because they're larger images, and we're not limiting ourselves to integer values, but you can actually watch the process of the convolution and the activation at each of these steps and the pooling, and then follow through all the way to the softmax activation that gives you the output in terms of a probability that this image of a cup here is an espresso. So I wanted to make that even simpler. And so I took that as inspiration and made a neural network that was so simple it could be performed inside an Excel spreadsheet. So the math is simple enough that the regular functions within Excel can be used to perform all of the actions that are needed for this neural network so that we now have a 39 parameter two-layer active convolutional neural network that classifies Tetris pieces. So here we've got a real sample where it's legitimate to depict these as zeros and ones. The color is just a guide to the eye, and we'll walk through that next. So if you go to the GitHub repository listed on the previous slide, you can download the Excel file that corresponds to what we're looking at here. And this is a series of 10 tabs that walks through the process. The first one, labeled inputs, isn't really an active cell. It's just a place that you can cut and paste Tetris pieces from as your input. So you can pick any of these, and then this is the filter that's going to be applied to that. So this is a 2x2 convolution filter with a 1, 1, and then a 0 and a 1. So the inference is the input where you are entering this piece that you want to analyze through the neural network to identify and classify it. So you can take one of the given ones from the first tab, or you can input something slightly different. You can shift this down, shift some of them left or right. And then the convolution step performs the operation to get the convolution. So this is simply the sum of the matrix multiplication of that filter to each step in that process. So that gives us a 4x4 matrix at the end of the convolution. We then do our rectified linear unit activation, and that doesn't change anything because all the values coming in were non-zero values. The next step is so simple, I didn't even describe it before, which is flattening. So that just takes that 2x2 matrix and flattens it to a single dimension. So now we have 2, 2, 2, and 1. The next step is the only part that's not self-contained within the Excel spreadsheet, and that is the weights that provide this network with the ability to make correct predictions. So these were generated by a training process. As I mentioned, the focus here is on inference, but you can use the same network to train with images. And that I did separately. And in that GitHub repository, there's a script that shows how that was done. But the result of that were the weights that give this neural network the ability to discriminate between those pieces. So those are then multiplied against the flattened outputs. So each of these cells here takes the flattened output and performs the operation against those dense parameters that we've calculated separately. And then these are used in the softmax classification step. So each of these softmax steps takes the output of the previous tab and takes the exponential of it and then divides it by the denominator, which was the sum of all of those. The denominator is listed on the right there. And then the final step is the output of the classification. And so in this case, it tells you that what the name of the piece was, and I pasted in that image there. So I'd encourage you to walk through that and adjust things on the initial inputs. You could try different pieces or variations of pieces at the inference step, and you can copy and paste those from the first tab, and you don't need to use the color. All it's taking from it is the 0 and 1 values.